Earlier we had a quick overview of GNSS. Today we are going to have a formal introduction to GNSS. We know that GNSS stands for Global Navigation Satellite Systems. So it is the collective term for all satellite-based navigation systems of different nations all over the world. So they are designed to provide user PVT. I am not explaining PVT, already discussed PVT, position, velocity and time. Time means the clock that the user uses can be corrected using GNSS time. That's why we say PVT. So they are designed to provide user PVT either globally means anywhere in the world, or regionally. Regionally means over a particular geographic area. Examples of global systems are GPS, the Global Positioning System of the USA, GLONASS of Russia. So these two are currently fully operational. Others are under development or partially operational. Then Galileo of the European Union and UK. Beidou of China. So these are 4 global systems. So using this global system, the user can determine his or her position, velocity or time anywhere in the world. There are also some regional systems, in fact 2 regional systems. QZSS, quasi zenith satellite system of Japan. So its coverage area is across much of East Asia and Southeast Asia. Okay, although it is a regional system specially developed for Japan, satellite signals are available in surrounding areas as well. Then the second one is IRNSS or NAVIC of India. IRNS stands for Indian Regional Navigation Satellite System. NAVIC stands for Navigation with Indian constellation. Okay. Now the coverage area of NAVIC is from 30 degrees south to 50 degrees north and 30 degrees east to 130 degrees east longitude. Okay. Of this, the primary coverage area, so it has two coverage areas, okay, primary and secondary. Primary coverage area will have all the satellites visible all the time, okay. The primary coverage area is over India and the region of about 1500 kilometers surrounding it. Okay. Now there is a difference between QZSs and NAVIC. Okay. Both are regional systems, but there is a difference between the two. NAVIC or IRNSS is an independent system. Whereas QZSS supplements GPS with 3 to 4 high elevation satellites. That increase the number of satellites in dense urban areas with high-rise buildings. And over mountainous regions. Okay, so it's not an independent satellite navigation system. It uses GNSS and in addition, it uses GPS, and in addition to that, it has its own satellites, high elevation satellites, which are particularly useful while navigating in dense urban areas with high-rise buildings on either side and also over mountainous regions. Okay. But NAVIC is an independent constellation under the control of India. Okay, in addition to this global and regional systems, there are some augmentation systems. They are called satellite-based augmentation systems. Okay. So what do? They basically augment GPS, mainly GPS. There is one system by Russia which also augments GLONASS services by transmitting additional corrections through one or two geostationary satellites. To improve accuracy and reliability. Okay. Now, since these corrections are transmitted using geostationary satellites, and a geostationary satellite has a fixed coverage area, a satellite-based augmentation system has a particular service volume in which only the user can receive corrections from these geostationary satellites. Now, there are multiple systems like this. WAS, Wide Area Augmentation System, was the first such system developed. By the US. Okay, then IGNOS. This is European. Global Navigation Overlay System for Europe. Then MSAS. MSAS is multi-function transport satellite augmentation system of Japan. Okay. And then the fourth one is GAGAN of India. GAGAN stands for GPS aided geo-augmented navigation of India. Then one SDCM system of differential corrections and monitoring of Russia. Now this one actually augments both GPS and GLONASS. The previous four systems augment only GPS. The sixth one is from China. Satellite navigation augmentation system. Now, it's not clear whether they augment GPS and Beidou or only GPS. Now, why these systems were developed? Okay, as I said, they transmit additional corrections to improve accuracy and reliability. Originally, these S-bus systems were commissioned to support aircraft navigation. Okay, since it's a safety critical operation, GPS or GNSS as a standalone system does not provide sufficient accuracy and reliability. So to improve accuracy and reliability, S-bus systems were originally developed for aircraft navigation. Okay, but any user within its service volume now can receive signals and additional corrections and improve accuracy and reliability. But the system was originally meant for aircraft navigation, okay, to support aircraft flight during different phases, including precision approach to landing. So approach to landing is very critical. Okay, accurate and reliable positioning is a must. Otherwise, it can lead to an accident. Okay, so we cannot use GPS or GNSS as a standalone system for precision approach. Okay, so S-bus can fill that gap. But again, S-bus cannot support all different types of precision approaches. So for that, a ground-based augmentation system is being designed, okay, which will be even more accurate. Now, we see that there are different S-bus systems, right? And for long-haul flights, an aircraft may have to go from one system to another, right? Now, the systems were designed in such a way that they are interoperable, meaning if the aircraft has an S-bus receiver, so to have an S-bus receiver, the receiver has to undergo rigorous certifications. Okay, simply any receiver cannot be used. So S-bus receivers are designed, and the augmentation systems are designed in such a way that with a single S-bus receiver, the aircraft can receive signals seamlessly from one system to another. So as it transitions from one system, say from for a transatlantic flight from US, it has to go from WAS to IGNOS. Okay, so it has to switch from WAS to IGNOS, and it can do that with a single S-bus receiver seamlessly without any outage in the service. Okay, this is why we say that the systems are interoperable. So these are all different GNSS systems. Now we also discussed that a GNSS system has 3 segments. Any question after this point? Okay, a GNSS system has 3 segments. Each of the systems, except for the even the augmentation system also has these 3 segments. GNSS has 3 segments. Space segment. So this is the constellation of satellites. The space segment is the constellation of satellites orbiting the Earth and transmitting GNSS signals towards it. Okay. Now in this class we cannot discuss all the different GNSS systems because although there are some common aspects, individual designs are different. Okay, so it's not possible to cover different systems. We will concentrate mainly on GPS and IRNSS in this class. Okay. We'll learn more about the space segment of GPS and IRNSS. Then second one is control segment. The control segment actually consists of a network of monitoring systems one or two master stations and a number of typically one or two again number of uplink stations. Okay. Now the rangings. What did I write? Okay, monitoring stations are located at precisely surveyed locations. Okay, so they are at now depending on the systems, the stations can be spread globally or they can be spread over a particular geographic area. Okay, but they are all located at precisely surveyed locations and they actually obtain range and range rate measurements to satellites. So all the monitoring stations have GNSS receivers installed and the receivers precise GNSS receivers, highly accurate GNSS receivers installed and they receive signals from the satellites process the signals and provide measurements, range and range rate measurements, and these measurements are sent to the master station. Okay, the master station post process. So this is offline processing. Master station post process all these measurements from different monitoring systems. Okay, and then they actually do reverse because the monitoring system locations are accurately known. Using these measurements, they determine the satellite position. Okay? Satellite positions in the orbit, then satellite clock corrections, and many other parameters. Okay, they have sophisticated estimation algorithms, and using post-processing techniques, they determine satellite position. Basically, the satellite orbits and satellite clock parameters. The satellites have highly accurate atomic clocks, but still the clocks deviate from GNSS system time. The the master station is also responsible for maintaining the GNSS system time. Okay, so they calculate the clock deviation, clock errors, satellite clock errors from the GNSS system time as well using these measurements. Okay, so many other parameters are also calculated. And then finally, estimated parameters such as satellite orbit, and then later we'll see how the orbit can be determined. Okay, so satellite orbital parameters, how the satellite position in the orbit can be represented, we'll discuss later. So after processing, they determine satellite orbital parameters, satellite clock corrections, etc., and upload all these to the satellites using the uplink stations. Okay. So typically once or twice a day uploading occurs using the uplink stations when the satellites are visible to the uplink stations. Okay, and then the satellites broadcast these parameters in the navigation data. We discuss quickly that the signal has three components: code, carrier, and navigation data. So all these different parameters are transmitted by the satellites in the navigation data. Okay. Okay. In addition to this, the master stations are also responsible for monitoring satellite health. Okay. They need to make sure that all the satellites are healthy. If a satellite is not healthy, then that has to be informed to the user. Okay, so master stations also monitor satellite health. and perform necessary satellite maneuvers remotely to keep the satellites in correct orbit. Okay. Uh, the third segment is called the user segment. So the user segment basically comprises the end users. Receiving GNSS signals to determine PVT. And the equipment and that the user uses for this purpose is called receiver. Okay, we'll discuss more about the receiver later. Okay, so these are the three segments. Now in this class we are going to briefly talk about the space segment of GPS and IRNSS. So we'll discuss how the satellites are placed in orbits, briefly about the orbits, and then the orbital parameters. Following this, we'll talk about the signal characteristics, signal structure, and unique property of code, which allows us to uniquely identify the satellites. Okay. We know that all the satellites of a constellation transmit their signals in the same band, same frequency range, right? But we can uniquely identify the satellites using code. Each satellite has its own code, unique code. And the codes are designed in such a way that uh, using them, we can uniquely determine a satellite. So we'll talk about that property, which allows us to uniquely identify a satellite using its code. And then we'll also talk about the navigation data briefly, and GNSS is time. Okay, so GNSS follows its own time. It has a different format than the calendar, day, month, year format. Okay, so they do not follow the usual format that we use. Okay, so they have different time format. So we'll talk about the GNSS system time, and that will conclude the discussion of the space segment. Then we'll move on to basically here I have not talked about the atmosphere, because the atmosphere is a medium which affects the signals when the signals travel through the atmosphere, right? Um, so we'll also talk about the effects of the atmosphere on the signals, and then we'll move on to the user segment. The user segment will mainly talk about the user receiver. So basically the chip, the GNSS chip that you have inside your cell phone is a small receiver. Okay. So whatever we'll talk about the receiver is done by that small chip. Okay. So we'll talk about the operating principles of the receiver, basic operating principles. Okay. So there are sophisticated things done, but we will not get into those things. We'll talk about the basic operating principles of the receiver. Okay. So this is the roadmap. Now, before getting into the space segment, let's talk about the applications of GNSS. Uh, Now, we use GPS or GNSS services in our day-to-day life without even realizing that. Okay. Um, Now, originally, GPS was developed for the military, US military. But over time, the number of civilian applications is much more than the military ones. Okay. It has far more civilian applications than the military ones. Now, GPS or GNSS services have become so critical, so essential in our life that they are considered a critical infrastructure of our society. It is estimated that an outage or malfunction of the system for a day or so can cost modern economies billions of dollars. Billions of dollars. Okay? But unfortunately, such a possibility cannot be ruled out because of some inherent vulnerabilities of the system. What are these sources of vulnerabilities? Satellites are far away from the Earth and they can only transmit signals with limited power. Because we cannot pump in a lot of power on board the satellite. There is a space constraint. So the satellites can pump in only limited power into the signals while transmitting that. And then signals have to travel a long distance to reach the user. So when the signals are received by the user, they are very weak. They are so weak that if you receive the signal and plot, you will not know whether you have received signal or not. You will just see some noise. Signal power is much below than that of the noise. Okay? And another problem is that the signal structure partly is known. Okay? So anyone with some expertise can replicate the signal. So signals are weak, partly the signal structure is known. Anyone with knowledge about the system and required technical expertise can replicate the signal. So using this, if somebody has some malicious intention, he or she can actually fool the receiver, okay, or jam the receiver. So they can transmit powered signals in the same band in which the GNSS satellites are transmitting signals. And then what will happen, since the signals that the person generate and transmit will be on the ground, so they will be more powerful, and the receiver, instead of receiving satellite signals, will receive those signals. So this is called jamming. Okay. Okay. When a receiver is jammed, at least you will know that the receiver is not working. There is something even more dangerous. It's called spoofing. So somebody can transmit GNSS-like signals exactly the way, because part of the signal structure is known. So they can transmit GNSS-like signals, and then the receiver will receive those signals. But since the signals are not originally coming from GNSS satellites, they have wrong information. And by processing those signals, receiver will give wrong position without saying anything. So the user will believe that this is his or her position. Okay, this is called spoofing. Jamming and spoofing are a threat. Okay, and moreover, signals are weak. Signals can be obstructed. This can cause outage during high dynamics. So there are issues. There are vulnerabilities, and we cannot ignore them. In fact, I saw a paper a few months back where the researchers studied GNSS signals received from the International Space Station and tried to detect such suspicious activities on the ground. Okay, so what they did was they received chunks of data from a highly accurate GNSS receiver on board the International Space Station. Okay, and then they received raw data. Okay, and then they processed the data and analyzed it. After analyzing, they found some suspicious activities. They do not know whether that was intentional or unintentional, but some suspicious activities were reported near Russia, in the Middle East, and in China. Okay. The space station has GNSS receivers on board. So they found that whenever the space station passed over those regions, the receivers were not behaving properly. Okay, the receivers noted some disturbing things, or they showed some anomalies, and this happened even when the International Space Station is about 1,000 kilometers away from the ground. Now you can imagine what would happen to a GNSS receiver on the ground, which would be much nearer to the source of such activities. Okay. We cannot ignore them, whether these activities are intentional or unintentional. We cannot ignore them, and they affect GNSS significantly. This is a completely different topic altogether. We will not get into that, but we should note that the system is vulnerable. Although the system is indispensable, it is vulnerable. Okay, so with this in mind, let's talk about the applications, and then you will realize what can happen if there is an outage or malfunction of the system. The applications are categorized into 4 broad areas. The first one is power grid system. Where GNSS system time is important. GNSS time is important. Now, why GNSS time is important? All the power grids must be synchronized in time. Okay. Why? Because if one portion of the grid requires more power, that can be delivered at precisely the right time from some other portions of the grid. Now, when there is a demand, we need to supply. We cannot delay it. And if there is a demand at a particular time, the other portion of the grid must be able to supply that at that time only. So for this purpose, all the grids, all different portions of all the grids must be synchronized in time. Okay, this is one reason why time synchronization is required. Another reason is that so we know that the power grid systems have generators that produce power or alternating currents. The alternating current produced by a generator must be synchronized in phase with all other generators. So it cannot be that one generator generates alternating current and then it is out of phase with some other generator. Now all the alternating currents of different generators must be phase synchronized. Okay. Now lack of synchronization implies a blackout. So it's important that all of them have currents generated in synchronism. They are all phase synchronized. Now, how do we achieve this? By ensuring time synchronization, we can make sure the currents are synchronized in phase. Okay? So these are the two reasons why time synchronization is very important for power grid systems. And for time synchronization, they use highly accurate clocks driven by GPS or GNSS. So such clocks are called GNSS slaved master clock. So they use GNSS slaved master clocks to derive the time. Okay. Then the second area is transportation system. Here we require GNSS PVT. Now, almost all modes of transportation systems now use GNSS. Whether it is railway transportation or marine navigation, civil aviation, UAV navigation, land applications, everywhere GNSS is used. Under land applications, we can note asset tracking. So for tracking assets, as it is transported from one place to another, GNSS can be used. Fleet management, car navigation, then pedestrian navigation, then finally we can also mention uh, guidance system, for visually impaired persons. Okay. The third area is financial networks. Where again GNSS time is important. So whether it is stock markets or ATM networks or internet banking, anywhere, while making any financial transactions, time plays an important role. You need to timestamp it. At this time, this transaction was made. What is the time? The time has to be accurate. It has to be universally true, right? I mean, all the different systems must be synchronized. There GNSS system time or GNSS time plays an important role. The fourth one is communication system. where GNSS PBT is important. We can give different examples where GNSS services are used. For example, location-based services. We discussed location-based services in the first class. So what do they mean? Now, suppose you have gone to some place and you do not know, you are new to that place and you need to find a particular destination. So be it a restaurant or ATM or any other important location. So you just, based on your location, you need to search for that and you will find the nearest one. How is this possible? This is possible because the GNSS chip inside your phone gives your current location. So these are the services which are rendered to you based on your current locations. Okay? So location-based services would not have been possible without GNSS. Then suppose you want directions to a place. So what you do, you give your current you just give the destination, and then the phone will give you the directions to that place. How is this possible? This is possible because GNSS gives your current location, which is projected onto a map, and then there is some pre-installed software in the phone which gives you directions to the location where you want to go. Okay. Then emergency services. Are possible with the help of GNSS. In the US, this is called E911. In Europe, it is E112. And I think in India, we have an emergency helpline number 110 or something. Most probably. So what happens, I'm not sure about 110, but I have read about E911 in the newspaper. Okay, so what happens when somebody is in distress, he or she would call this number, okay, E911. And so in the newspaper, of course, they would not say the details. Then the help arrives almost immediately. There were several such incidents. So basically, what happens when the person calls this number 911? Okay. So in his mobile, in his or her mobile, he or she has to dial this number 911. When this number is dialed, the GNSS receiver or the chip inside the phone transmits its location to a secure server. Okay, and then the E911 operator can retrieve this location from that server, and then based on the requirement, the help would be sent. Now, for the help to arrive in time, the location has to be known correctly. Many times, such incidents or emergencies occur inside the building. So, determining the location accurately, very accurately, is still a challenge, but work is going on in phases to improve the accuracy. E911 is operational in the US and it is used extensively and it is quite effective. Similarly, Europe has E112. I think I have not read about that, but I think it is also effective the same way. In India, we have 110, most probably the number, helpline number, but I'm not sure how effective that is. But there is a helpline number that we can use or try to use in case of emergencies. So all of these would not be possible without GNSS. Okay. So these are the different applications of GNSS. This gives you an idea about the extent with which we use GNSS in our everyday life. And I also told you about the vulnerabilities. So if the system is out of operation for a day or so, it will affect us greatly. So with this in mind, we'll stop today and we'll continue tomorrow. Okay, that's it.